Hello. So we are going to talk about some magnetism, or this is going to be the first of a few videos about magnetism, try and digest it into little bits and pieces. So the first thing we're going to do is I'm going to share my screen and I'm going to put my camera on so we can just look at some demonstrations. And from there, we're going to develop some ideas about magnetism, specifically in connection to our understandings about gravity and the electrostatic force. So we want to see how it's similar to and different from. So let me share my screen so we can do that. And I'm sure we're all familiar with magnets, right? Put them on our fridge, etc. Um, Other times and places that we've dealt with magnetism, but I'm just going to put a whole bunch of what's going to look like stuff here on my white page, and we can kind of go through that. All right. So here's some stuff, good stuff. All right, great. So I have all this, I don't know, nonsense looking stuff. But let's just start playing with what we've got here. Whew, things are going to go all over the place. So here we go. So I think we're comfortable with the idea of magnets, right? Like, so if I pull these apart, snap back together, I think the important thing we see here is some attraction. If I flip that around, we can actually, I know that you can't feel this, but I'm trying to push these together and they're not going. So we have this idea that magnets can both attract and repel. That should be a fairly comfortable notion here. So notice here, this side, uh, repelling, and then if I let that, if you notice, what did that magnet do? That object is flipped around, right? The other thing you notice here is that these things are exerting forces over a distance. So that brings us to our first sort of idea, and I'll clean off this later after I do a bunch of stuff showing you what's going on here, is that magnetism is a fundamental force. Is a force that acts over a distance. As the magnets get closer, that force gets stronger. So there must be something, about these that makes the magnets. We'll kind of get into that. But there we go. And the other thing we can see is that this force attracts as well as repels. And if I actually got this right, I could almost try and float this on top here. That'd be really hard. I'll probably just spend too much time playing with it. But there you go. Oh, it's kind of hard to see, but I'm like able to keep that there and see it fly through the air. But the idea here that it is a non-contact force, so it is a fundamental force. And so that makes sense that with all of their fundamental forces, when the things are closer, the force is stronger. When it's further apart, the things are weaker. Okay. But the next thing we want to look at is like, well, what gets affected by magnetism and what doesn't? So I've got this thing here, which is actually a decently strong magnet. I'm going to clear off some of my space here. And what I've got here is an iron nail. You can see that that iron nail is being attracted. And actually notice both sides of this iron nail are being attracted, which is a little different than what was happening with this, where it was getting repulsion and then attraction. Notice here I have a penny, nothing. Notice here I've got a tuning fork. And you don't know because you're not in the room, but this tuning fork is made of aluminum or aluminium, if we're going to say it properly. And there's no attraction there. I've got just a regular old pen here, plastic, nothing going on. I've got my skin, nothing's going on. I've got this chalk, nothing's going on. I've got paper, nothing's going on. Once again, this coin, penny, pennies are made out of zinc with a little bit of copper overlay, nothing happening. But notice that iron, boom, there. And then I've got another thing here, which I'll show you. Kind of pull out this bad boy there. Let me zoom in a little bit so you can see it. That's not so clear, but there you can see what that is. I don't know if that's, you can see there, it says 5 cents on it. It's a Canadian nickel, right? Watch. The Canadian nickel is attracted to my magnet. The Canadian nickel is made out of, well, easily enough, nickel. Okay. Whereas here's a dime, once again, that's made out of zinc, nothing going. So it seems like only certain materials. Oh, there you go. And what do you see there? Little iron piece, and that works. This little ball, iron as well. So what I hope you're seeing here is that certain materials are not affected by magnetism at all, and certain materials are. Some materials we're getting attraction repulsion, some we're getting only attraction. So that should have a lot of resonances with some things we've said in the past. So here we go. Let's take some notes about this. So the first thing we have here is I'm going to kind of talk gravitation versus electrostatic versus magnetism. All of these, we know that these forces are fundamental. Okay, so what does that mean that they're fundamental? That means that they're non-contact, that the force exists even when there's space between the objects that are experiencing them. Another thing about fundamental forces we know is that the size of the force then diminishes when the two things interacting are further apart and gets stronger, really strong when they're closest together. Another thing we could probably say about the magnetic force, right, is that, look, this object's not moving and it gets closer and it gets faster, right? Hopefully that kind of like reminds us of the same thing like a mass that falls down to the ground or a charge that approaches a negative charge that approaches a positive thing and it speeds up, right? That work is done on it. There's another thing that's in common with all these forces is that they're all conservative forces. There we go. All of them are conservative. And what does that mean? That means that there's a potential energy associated with them. And that also means that there's a field associated with them. And that should make sense in the area surrounding this object, right? Other objects that are going to be affected by magnetism will feel a force. Okay, so those are consequences of this force being conservative. But there's some important ways in which they are different. The gravitational force only attracts, right? But we know the electric and the magnetic force can both attract and repel. And that's super important because we connected that with an idea. We connected that idea with flavor, right? Gravity only attracts because there's only one flavor of mass. Okay. We're going to see, we know that the electric force attracts and repels because there are two flavors of charge. And so that sort of leads us that there's two flavors of something for magnetism, but we don't know like what the what is with that, right? So there we go. The next thing that we want to say here is an important, like what causes these things? Well, what causes gravity? Like, why does gravity exist? And gravity exists because of mass, right? An object with mass exerts gravitational forces on all other objects with mass. That's the essential idea of Newton's law of universal gravitation, okay? So the cause of the electrostatic force, well, what's that? Well, we know what that means, what that is charge. So when an object is charged, it causes electrostatic effects on other objects. So the cause here, it seems to be not all things, right? It's whatever this magnet is the cause, right? So some sort of prepared magnet. We should probably say, the cause of charge is prepared objects as well, because we know that charge is not a permanent state, that objects don't kind of like quote unquote want to be charged. They're always trying to seek neutrality. And so you have to prepare an object to cause an imbalance of charge. So I'm actually going to put that in an imbalance of charge, right? I need a net charge on an object in order for it to display the electric effect. So the cause here is we need a prepared magnet. We need something that is magnetized, seemingly. That's what we've seen so far, whatever that means. So we have different words then for what it means to be prepared for electrostatic charged and be prepared in magnetism, which is magnetized. Okay. Now, what does it affect? Well, we saw, sorry, what does it affect because of the way so I'm not doing cause effect here. I'm doing what is causing and then what objects are affected by the mass. So with gravity, we saw all other masses were affected by mass, right? Minimum requirement for there to be force is two objects. And with gravitation, it's two objects with mass. So what does that prepared object affect? And we saw all other objects, right? Because, oh, let me just move that up. All other objects. We saw that if I had a prepared positive charge, right, that thing would attract negative charges, would repel positive charges. But we also saw that it would interact with neutral objects and polarize them to cause them to be attracted. So that's why I'm going to say all other objects. But what does it affect? What we saw here is it only affected metals, and not even all metals, only some metals. Okay. And specifically, which metals did we see? Well, we saw iron, Fe. We saw nickel, Ni on the periodic table. And I don't have an example of it here. Well, I do. It's actually what this thing is partially made out of, but you wouldn't be able to look at that and go, oh, I know what that is. But I want you to think about nickel and iron for a second, right? And I want you to think about, and I'm sorry to do this to you to make you think about the periodic table, but I want you to think about the periodic table. And if we were to look at the periodic table, what do we know about nickel and iron? Okay. Hopefully, what you said to yourself is that we know that they are both transition metals. So the reason why I'm looking down is I'm trying to pull up on my phone a copy of the periodic table. Okay. So we said nickel, excuse me, let me blow that up. Iron is there, nickel is there, and then right in between them, what's that? That's cobalt. Cobalt is another metal that would affect them. Okay, great. So there we go. Iron, nickel, and cobalt. And we should expect, by the way, in the periodic table, that if iron is affected and nickel is affected, that cobalt would be affected as well, because the organization of the periodic table is that things in the same group tend to have similar properties, and things in groups that are near to each other have properties that are more similar than in groups that are far. So it should make sense that if the group that nickel and iron are has this effect, so would the group in between them. So I'll just go by that logic. We're not going to get too deep into that. But we're going to use that idea and come up with a name. The first type of material that was seen to have the magnetic effect was iron. And Fe stands for ferrous, right? So these materials were named the ferromagnetic materials. Okay. So the ferromagnetic materials are nickel, iron, and cobalt. And our definition here is these are materials that can be magnetized to become permanent magnets. In the same way, I can also say these are materials that are attracted to all magnets. In the same way that we have an unprepared material is attracted to all charge, it gets polarized, and then that object is attracted. We're going to say that unmagnetized ferromagnetic materials are also attracted to all objects. But there's something interesting here about magnetism, which is that's different than the electric. So we're going back to that comparison. So I'm just going to take a little jump back. Gravity, electric, magnetism. If I have, a negative here and a positive here, we know that those two objects attract. Separately, I know I have a positive here and a positive here. Those objects, will repel, because like charges attract, opposite charges repel. But here, I've got something very different. This is attracting, but if I take the same object and flip it around, now they repel. It's almost like with the same object, one side of one attracts one side of one, and one side of one, the same side of that uh, first object repels from the opposite side of the other object. So that's very different. And what we're going to say then is therefore magnets are what are known as polar, right? All magnets have two sides, right? And so the flavors that we're going to have with magnetism are not about positive, negative, but these two sides. Okay. Now you probably know what the sides are called by now, but we're going to get there about like how we call those sides through a quick historical lesson in a moment. So the last thing we want to talk about in this video is that particular piece. What are those sides called? We're going to do that by talking about the fields themselves. So the gravitational field. What defines the gravitational field? Oh, I'm sorry, not what defines the gravitational field. What defines the direction of the gravitational field at any point in space? And hopefully what you remember, just to come down here is, I'm going to actually go to a new sheet of paper so that I'm not squishing at the bottom. So gravity, electric, magnetic. The gravitational field field's direction, that's better, is defined to be the direction of force on a hypothetical test mass at that location in space. Okay, right? We put the mass there. If I have like a big, sorry, if I have a big mass here, a little bit of mass there, it would go this way, a little bit of mass there, it would go this way, a little bit of mass there, go this way, so on and so forth. And we got that idea of the gravitational field. So how did we define the electric field? So the electric field is defined to be, now here we have to be a little bit more specific because we had two flavors of things that were interacting. The direction of force on a hypothetical positive test charge at that location. Okay, which is why if I had a positive thing in the center, a little positive thing there, and this is what would happen, right? And we saw then that I've had a negative thing in that same in a space there, that the field would all be radially inward. Okay. But the force on a positive test mass, test charge is how we defined the electric field. So how, therefore, do we find the magnetic field? And to do that, here's our history lesson. There was a culture that discovered magnetism a lot earlier than other cultures, specifically in like the 2000 BCE era as Westerners do time, and that's our little hint, discovered magnetism. And that culture was the Chinese culture. And it wasn't even done by on purpose. It was done happy accident to discover magnetism. The way that I heard it was reported that shepherds out in a field, bored watching their flocks, found these little red rocks, and the red rocks would like stick to one another, right? Or repel, and they could play with the rocks and just push them around, and like it was just something to do to pass the time as you were going along, right? Red rocks, red, red, red. Oh, that's right. Iron, when it rusts, iron oxide is red. And so those naturally occurring magnets out there, that was the first person to discover them. One of those shepherds, in some sort of ultimate fear to boredness, took a string off the bottom of, I guess, their tunic or whatever would be the appropriate name for that piece of clothing, and hung the rock on a string, and noticed that whatever they did, that one end of that rock was always pointing in a very specific direction, and the other end of that rock always pointed in the exact opposite direction. And those directions were north and south, right? So what did that shepherd invent? Hopefully by now you understand that what I'm talking about is the compass. Okay, because all a compass is a magnet, in this case, suspended in a fluid and able to rotate. But I could just take one of my regular old bar magnets and tie a string on it and suspend it there. And the important thing there is that all magnets have two ends, and those two ends are called the poles of the magnet. So all magnets have two poles. So the flavor of magnetism is going to be the polarity. So going back to that, right in the beginning, two flavors of polarity, where the two flavors of charge were positive and negative, the two flavors of polarity are called north and south. Okay? So one end of the magnet is called the north pole of the magnet, one end is the south pole. The north pole of the magnet used to be called the north seeking pole, because that would be the part of the magnet that if you suspended it on a wire would point towards geographic north. And that's on this compass, that's this red arrow here. This is pointing towards geographic north. And where this one is pointing to geographic south, it's called the south seeking pole. Now we just call it the south pole of a compass. And so this was the first device that we used in order to see magnets. And then we also noticed that if I bring another magnet near my compass, that it started pointing in different directions. And therefore, we came up with the following definition. The direction of the magnetic field at any point in space is the direction the north pole of a compass would point at that location. Okay, the direction, the north pole. So our compass becomes our detection device for magnetism and defines the direction of the field. And I got to just stop here and say that is very different than what's happening here in gravity and electrostatics. Both gravity and electrostatics are defined by the direction of force on an object. This magnet is not like, or this compass is not like moving left, right, up, or down as a function of being in the field in the same way that a charge would. Instead, what's happening here is that the compass rotates to align with the field instead. Okay? So this is defined in a very different way than the others. And that's going to have some major implications for what the shape of the magnetic field looks like compared to the shape of the gravitational field and the shape of the electric field. Because I think we could look at these and say there's a lot of similarities between these fields where this field is always converging. This field can converge or diverge. If I have multiple charges, we saw how those fields interacted. So that's what we have so far. The last thing I want to say is, oh no, I will deal with that actually in the next video. So we have a basis for an understanding about magnets. All magnets have two ends or poles, north and south. And we will go through the specifics of magnetic force and then what these field looks like from there, and then be able to jump out to answer the question, well, what is it about this object that causes it to have magnetic fields where, say, for example, my aluminum thing doesn't, or my copper thing doesn't, or, even my piece of plastic doesn't. So that is something we'll discuss very soon.